So you use the word, sorry, you use the word cocoa peat, but the technical term for that is coir, right? Peat is another thing. Sphagnum peat mass, that's a different thing. So peat is a different media, coir is a different media. Okay, come on. So we're going to learn about soilless substrates. So who has used? Have you anybody used cocoa peat before? Have you? So what do you know? What do you know about cocoa peat? Tell me anything you know about it.
It is basically made from coconut shell.
It's made from coconut, right?
It is a majorly comes in commercialized. It comes in blocks,
Yeah,
and we use it for as a sterilized medium because it doesn't have any bacteria or any microorganisms.
correct.
So mostly we are using it for nursery raising, and somewhere we are also using it for cultivation.
Cultivation too. So they're using cocoa coir for.
But along with vermiculite and perlite.
I'll let you add them, right? So we'll get to that. Okay, that's good. What else can anybody add?
Water retention.
Water retention. You like it because it retains more water. Okay. Yeah, yeah, brownish black in color.
Reusable.
You are you reusing it? Okay, so do you clean it and reuse it? Okay, okay, that's good. That's environmentally very responsible, right? Okay, so that's good. So some of you have some idea about the soilless substrate. Some of you have seen them, right? You are telling the color of them, right? So what we're going to do today is we're going to go deep into the soilless substrate, right? We're going to look into their physical properties, some of the chemical properties, right? Kind of like you are looking 1 mile deep into the, or 1 kilometer deep into that, something like that, right? Learning everything about it. So you will be able to tomorrow make a judgment on, okay, this is coir, this is peat, that is vermiculite, this is perlite. How do I combine? What happens if I do this versus that? So that type of strong knowledge is what I'm going to try and give you. There is one caution. This is technical content. Okay. When what I'm hearing is that there is a lot of technical content here going on, and that may be sometimes troublesome. But the fact is this: the fact is this is advanced science, and when it's advanced science, it is going to come with technical content for you, right? I am trying to teach it at the really basic level. That's why it's called basics of soilless substrate. Okay. Uh, I can go below that level and kind of just, what they call, brush it off, but I'm not doing justice if I do that. Because what I want to see is, I want you to get that extra knowledge that you're missing. That knowledge comes from research and practice. This research and practice is being done in the Western countries for a very long time, and I'm trying to bring that knowledge and give it to you. If I have to just brush off something, you don't need me. Anyone can teach it for you, right? So I'm going to try and still keep the technical content, because otherwise it's not justice. What you can do is, in case if you feel it difficult, if it's not going through clearly, don't hesitate, stop me. This is your opportunity. You are the select some 15-20 students in the entire country who are listening this for the first time. I know there are courses in protected horticulture, things like that, in universities, in horticulture departments. They are not this depth. I've seen them, I've worked with them. What you are hearing is research-based information. So take it as an advantage, as an opportunity for you, right? And ask me questions. Slow me down, tell me, sir, I don't understand this. It's okay, we can discuss more. There is some easy content here, but towards the end you start getting little bit into the thick of that technical content. All right, we'll go slow there, but pay attention, and if you are not catching it, ask me questions. That's important. Asking questions is important. All right, okay, I'm going to step up on the stage and then start moving like yesterday. um, Play current page. Okay, so the first few slides are easy. First few slides are easy to go through. So here is some just fundamental information, easy to read. The thing is, I want you to remember is until 1960s, in greenhouses we were using regular soil. Because around 1955-56 is when the soilless substrate started to become available. Some research was happening in the United States. But until 60s, people were using simply soil. They used to fill, I mean, even probably today in some greenhouses, maybe they're filling, loam and sand and that type of soil. But we'll learn about that, why it is not good. I'm going to show you that slide. But around 60s is when they become popular. But until that time, they were using loam, organic material, organic media, and then some sand. They used to mix them and put them in a pot and used to grow plants. But then these became popular because of these four good reasons. These are very important reasons. Look at this. Reduced pathogen infestation. You said they're already sterilized, isn't it? They are sterilized. There could be a little bit of pathogen, but compared to regular soil, very little amount of pathogens. So number one advantage, root-borne pathogens won't be there. It's nicely sterilized. You don't have to face those problems. Nematodes, things like that are a big problem, and you won't find them in this. They're nicely sterilized. So that's one advantage. It's a light in weight. Light in weight is important because when you grow, you are a greenhouse grower. You are a greenhouse grower, and you are growing materials. Let's say maybe not in your case you're growing fruit, but there are greenhouse growers who produce seedlings, pepper seedlings, tomato seedlings, and their job is only to produce seedlings. They don't produce anything more. These seedlings are sold to other growers in their greenhouses. They grow bigger plants, right? So if you are just doing in the business of seedling production, you have to ship them to growers all over the country or farmers all over the country. Shipping is expensive, isn't it? Shipping goes by weight and volume. And if you're using regular soil, it is heavy. Soilless substrates are light. I think if you have used them, you would have felt it already. It's pretty light. It's like literally like water. So that's one big advantage. Transportation costs go down simply because they have less weight. Okay. Sometimes people, I do not know how advanced it is, but in many Western countries, they actually ship pots, chrysanthemum pots, potted plants, big potted plants. People buy potted plants. They just want to plant them like that. And if you are shipping a big potted plant, it's going to be heavy if it is full with regular soil, and it's going to cost you more. So that's one big advantage. Okay. Easy customization. You just said, peat, vermiculite, perlite, coir. You can mix them whatever way you want and create your own nice mix. Because when you add these organic and inorganic components, and later on you will see all those examples, but when you customize them, you can change water holding capacity, you can change nutrient retention capacity, things like that. So you have that flexibility. With regular soil, no, it comes like a already pre-made substrate. You can't make any big changes there. So that's another big advantage. And this is one very, very important, uniform composition. When I sell peat to you or coir to you, you are assured that it is coir or it is peat. Or when I say it has got 80% coir, 20% vermiculite, you're kind of assured because it is mechanically mixed. So there is some uniformity there. So the reason why this is important is the greenhouse farmers, growers, they do the business year after year after year. This year, let's say you started with a medium, you started with a medium, it's got 80% coir and 20% peat. The next year you would expect the same composition because you've already prepared a cultivation practices, and you know how to grow, you know how much nutrients you have to apply, you know how much water to apply, you learned all of that. But then all of a sudden, let's say next year, you get a different medium, different substrate, 60% coir, 20% vermiculite, 10% something else added to it. Everything changes. Now you have to reinvent the wheel, what we call reinvent the wheel. You have to again go back and figure out which is the best nutrient recipe, which is the right amount of water. That's not good for farmers. You already prepared a recipe and you want to follow it, right? So these substrates are uniform. When a company is selling it, they are telling that this has got 80% coir and 20% vermiculite, and we certify that. If it is not there, you can legally challenge them, right? So they're going to make sure that it has got at least what they're saying on the bag is inside the bag. So that's another nice thing about it. So very simple stuff, right? But then there are also some functions that are very, very important for the soilless substrate. It is a reservoir of nutrients. It's very touch sensitive. It holds water. Aeration is important. Come on. It provides a lot of aeration. and it's also important for anchorage. So the thing that I'm trying to say is, although there are a lot of advantages compared to regular soils, they provide the same functions that the soil would do. A soil would provide nutrients, right? A regular soil would provide water to plants. A regular soil would provide air inside. And a regular soil also helps in holding the plant, anchorage. The same functions are also possible with soilless substrates, but with some additional benefits. That is why they became popular in 1960s. And since then, we use soilless substrates. Okay. For those who came a little bit late, we are talking about soilless substrates. Cocoa peat, whatever you call it. That's what we're going to talk about. We are going to dive deep and understand a lot of things about them. So tomorrow, when you go to market, you can actually make your own decision. Okay, I don't want this. I want this because it has got A, B, C, D benefits. Okay, that is my goal today. All right, but we'll go deep, very deep into this. I also told others that there is some easy content initially, but as you go towards the final slides, it can get little bit technical. Okay, but challenge yourself. Challenge yourself. It's not that big of a deal. Let's learn a little bit more advanced stuff. Okay, that's important. All right. Okay, that said, let's. I got a lot of good pictures. So if I'm talking something, there is a picture that supports it, so you can easily understand that. Okay. So now let's go to some basics. Here I'm comparing a regular soil, okay, and a soilless substrate. Two things. There are two characteristics. One is called pore space. Okay, we'll talk about that. One is called pore space. The other is just the solids. Okay. Now, before we understand this graph, let me explain what are those two characteristics. So, if you look at soil, all right, let's say you take a little bit of soil and put a magnifying glass or a microscope, you know what you will see? You will see two things. There is sand or clay, solid material there, but between them, you have gaps. Those are pores, pore space. This pore space is very, very, very important. This is where everything is happening. Water is in that pore space. Nutrients are in that pore space. Oxygen is also in that pore space. That pore space is so important. But you will see that maybe you may not see it when you are looking at your with eyes, but when you kind of use a magnifying glass or a microscope, it kind of starts seeing pore space. That is pore space, and the solids are just the sand particles, the clay particles, all of that. They're solid material. That is what I'm showing you here. Now look at the regular soil. Pore space and solids are nearly same, right? 50-50. But now look at the soilless substrate. What is the biggest difference? What do you see from that graph? Who can interpret that graph? So if you have more pore space, why is that good? Nutrients. See, that is the advantage of that. You can hold more water. You said more water, right? You can hold nutrients. You can hold more air in a soilless substrate compared to a regular soil. I usually make this funny joke when I talk about this in my class. So let's say you buy soilless substrate. You buy in a bag, right? You buy in a big bag. I'm telling you that 75% of that is what? Pore space. There's nothing in it. So you're paying for nothing. 75% of what you're buying is nothing. Empty pore space, right? But you're paying for that. Right? It's just an interesting thing. But very, very important. You got a lot of pore space. Point to remember. Now, that same pore space can also be expressed as in a percentage way, like a porosity. That's the term. The first important term I want you to remember is called porosity. Porosity, it's a percentage. It's a percentage. So what that means is, let's say I have a bucket, okay. This bucket is 1 liter in volume. 1 liter. Everybody understands, right? 1 liter in volume. So I fill, please come. I fill in this 1 liter bucket cocoa peat. Okay. So what is the volume of the cocoa peat now? 1 liter. because I filled it all the way. But I'm telling you that pore space is what? 75%. So what is the volume of pore space? It is 1 liter, right? Out of that, 75% is 750 milliliters. Very easy, right? You can easily calculate 750 milliliters. Now, the total volume is 1 liter, 1000 milliliters. Pore space is 750 milliliters. Express that pore space as percentage now. 75%. That is porosity. That's all. Porosity is pore space expressed in percentage. Is it simple? That's it. Okay. Remember that. That's the first term, porosity. All right. Now, inside, we'll talk about those pores and we'll understand those pores because those pores are very, very important. There are all kinds of pores. There are big pores, wide pores, narrow, small pores, all kinds of pores. The wider the pores, they are good for air. The pore is wider, I mean, it's not this wide, it's kind of microscopic still, right? But if it is wider, it's good for air. But if it is narrower, it's good for water. Okay, just keep that in mind. More information in the following slides. But what we want to do understand is, okay, we have pore space, very good amount of pore space. How much of the pore space should be occupied by water? How much of that pore space should be occupied by air? This is very important dynamic. If you fill all those pores with water, that's not good for plants. Yeah, because roots need oxygen. Roots have to grow, and further they need oxygen. Where are they getting the oxygen from? The roots are getting oxygen from the pore space. So if your pores are all filled with water, it's like waterlogged condition, right? And they're going to die. So you want to maintain some amount of air in that pores. An ideal combination is 25% of the pore space should be air space, 75% of the pore space should be water space. Okay, so now let's do again a simple math. Again, 1 liter bucket. We filled 1 liter bucket with cocoa peat. So the volume is 1 liter cocoa peat. 75% is porosity. So how much is pore space? 750 ml. So far we understand that, right? Now I'm saying out of that 750 ml, 25% should be air, another 75% should be water. So can somebody do calculator and tell me what is 25% of 750 ml and what is 75% of 750 ml?
562.5
About approximately 560 ml of water, and then remaining, how much is that? About 190 ml of air. See, now I gave you some numbers now. Started with 1 liter bucket, filled it with cocoa peat, 1 liter cocoa peat. 75% of that is pore space, the rest are solid cocoa peat particles. Out of the 750 ml, you calculate what, 590 as water space, and the remaining 25% as the air space. So this is inside the pores. This is how it should be. Ideally, this is what you want to maintain. 25% of the spores should be air. Otherwise, plants won't grow well. Okay, remember that. All right, people are coming slowly. Come. I think so far it's easy. So those who have joined a little bit late, everything has been so easy. Couple of slides, you can easily read the slides. Okay, we are talking about soilless substrates. All right, soilless substrates, coir, peat, things like that. All right, but you can read that stuff. It's very easy stuff. But understand, porosity is pore space expressed as percentage, and in that pore space, 25% should be filled with air. Remaining 75% ideally should you fill it with water. Okay, got it. All right, so here are some examples. There are two different types of soilless substrates. This is peat plus perlite. Perlite means, I don't know whether you use perlite in India. It's white color. You do? Okay. So it's basically it's it looks like popcorn, tiny popcorn particles. And now you will learn about perlite and its properties later. But when you add perlite, it creates big pores. When you add perlite to substrate, it creates big pores. And those big pores are for what? Big pores are useful for air. So when you add perlite, what do? You increase what? Airspace. Okay. So if you buy media and you notice that the media is pretty compact, then what do? You simply add perlite. You are customizing it. See, that's one of the advantages. You can customize it, right? Perlite increases airspace. See that this just an example. You notice here there is another media where I have peat, perlite, and vermiculite. Little bit of bark is also there. We in the US we use pine bark. Like when you are driving on the road, you will see lots and lots of pines. It's always this wild forest of pines. So we have plenty of pine trees. So we use the pine bark. We can take the pine bark and we have prepared, just like you prepared coir from coconut, the pine bark is from pines. Okay. So we add that, especially in nursery, ornamental nursery industry, bark is used. That's what it is used here a little bit. But you can see there are all kinds of customizations. Okay. Water space is 72%, right? Remember 75 is what I told you. It's pretty close, 72%, 28% airspace. Pretty close. Little bit less here. More airspace. Why? Read the what is inside, read the composition and tell me why there is more airspace. Yeah, everybody understands that? When you add more perlite, what are you increasing? You're increasing airspace, and that's exactly what happened, 40% airspace. This media is pretty light and it's got only 62%, okay, water space. Just some examples. Easy slides, right, so far? Okay. All right, now comes the question. You may ask me, sir, why are we worried about soilless substrates? They're good, but they're expensive. I just want to put soil. I have plenty of soil in my nursery. I'm going to dig it and fill it in the pots, and I'm going to grow plants, right? You can do that, right? But you should not do that for some good reasons, and that's what this slide is explaining. Okay. The biggest problem, if you put regular soil, loamy soil, clayey soil, whatever soil you have in a pot, is the biggest problem comes from drainage. Drainage. So let's talk about drainage. Let's talk now about regular soils. So you add water on top of the soil. Let's say rainfall happens and the rainwater drips slowly down through the soil, right? It is draining down. If the soil is deep, like 1, 2, 3 meters deep, all the water drains down. So there is not much of water logging conditions at the top. So the drainage is dependent on the depth of the soil. The deeper the soil, the better drainage. Now you take that soil and put it in a pot. How deep is a pot? That deep. So I just told you that if the soil is deeper, then you get a better drainage. If the soil is not deep, the drainage is not good, so water logs. It's not good situation for plants. But the pot is so small, 30 centimeters, you won't get any good drainage in that 30 centimeters. You need 2, 3 meters deep to get good drainage. So when you take soil and fill it in a pot, 30 centimeters tall, you won't get any drainage. All the water logs there. And then when water is logged, the plant growth is very, very bad, because all those pores are now filled with water. There is no air. There is no 25% air. This is the one physical reason why we should not fill soil in pots and grow plants. Okay, because of the poor drainage. Remember that. Okay, does it make sense? Drainage, depth. You need the depth for drainage, and there is no depth in the pots. In the other reason we already discussed, when you fill it pots with regular soil, they're heavy. Transportation costs, a lot of costs in transportation. That's the reason why you have to use soilless substrates in pots. Do not fill them with regular soil. You may grow some plants, like even my house, and I go to my mom's house, my mother's house in Bangalore, I saw she has rose plants and all the pots are filled with soil. And she doesn't even know about soilless substrates or anything. But that's what they know. From olden days, they just fill them with soil. Yeah, you can grow something, but they won't grow well. They won't grow well because of the same reason. There's a poor drainage there. Roots are not getting enough oxygen. Okay? Now that makes sense? All right. All right, now we're getting into a little bit details. The first thing we want to ask the question is, why is that pore space really important? I've been talking about pore space, pore space, pore space, right? Right? So why is that important? Okay, so you have to now assume that this is, you know, a sort of like a transverse section of a soil. Okay, there are some solid particles. Maybe this is cocoa peat. Okay, that particle, cocoa peat particles here and there, and you have put it. So this, that's the pore space, right? That those empty gaps between particles, that's the pore space. Okay, does this picture make sense to you? You all understand, right? See what's going on here in that pore space. The pore space is the functional part of a soilless substrate. This is where everything is happening. The solid matrix is just there. Inside the solid matrix, nothing happens. It's solid. All the activities, you know, the nutrient absorption, solubility, water, air, everything is happening in that pore space. Pore space is the functional part of a soil substrate. Okay, what's happening here? Notice here, those nutrients, they could be nitrogen, phosphorus ions, potassium ions, whatever they are attached to that solid matrix, and periodically they will come into solution, the water in that soil phase. When they come into the water, they become soluble. That's what it means. They become soluble. So let's say this is cocoa peat solid particle. You have those fertilizer ions attached on the side. At some time, they release and get into the water outside in that pore space. When they enter that water, they are now soluble. Unless these ions are soluble, roots cannot take them. Roots cannot pull the nutrients from solid particles, attached particles. No, they cannot. Roots only can take nutrients which are in water. Very, very important. Remember that. So the exchange happens periodically. When you apply fertilizer to the soil or soilless substrate, some fertilizer is in this water, but a lot of the fertilizer gets attached to that solid particles, and slowly those fertilizer ions get released into the solution. And as they get released, they become soluble, and then roots can take. Actually, roots grow into those pore spaces. Those tiny young roots, they have to grow, right? They can't grow into the solid particles, right? They grow through those pore spaces. And as they are growing, they take the water and the nutrients from the solution. You see the dynamics, what's going on inside the soil? That's what happens. So it's very important for nutrients. It is important for water. It's also important for air, right? You see here there is a pore. In this pore up to here there is water, and there is nothing here. Well, it's not actually nothing. There is something there. What is that? Air. And then air has what? Oxygen. That's what roots need. So if the root is growing like this and comes over here, there is plenty of oxygen, takes oxygen, grows further. Nutrients, oxygen, water, everything is there. That is what is happening in the ground. Okay? That's a very dynamic world. Okay? But pore space is one that is contributing to that. They cannot grow into this part, right? Into this big solid part, roots cannot go into that. It's hard. Okay? So that is why it is so important. Right? I will also mention something. There is a term called hygroscopic water. Hygroscopic water. See, you see this water here, the blue color thing, that's water, right? That water is in the pores, so roots can easily take that water. But sometimes a thin film of water gets attached to the solid particles. It is tightly bound by the solid particles. Roots cannot get that out. Roots cannot extract that water. That's called hygroscopic water. We don't want a lot of hygroscopic water, again keep in mind, but I just want to give you the term. So if you hear it somewhere, hygroscopic water, there is pore water and there is hygroscopic water. Pore water is, that is blue color, roots take that. But if it is hygroscopic water, it is such a tiny thin film, it is very hard for roots to extract that water and absorb it. Okay. Any case, you just remember the term hygroscopic. This is why pores are important. They are the functional part of the soilless substrate. They make the nutrients available to plants. They make water available to plants. They make air available to plants. So the more pore space, better for plants. And you get more pore space in soilless substrates compared to regular soils. Okay, so far connection. Okay. All right. Now let's talk about what are the different types of pores. So we know pore space is important. We know that soilless substrates have more pore space, get it? But are all pores same in size? Are they different? If they are different, how can we group them? Generally, pores are grouped into three categories. Three, okay? Macropores, mesopores, micropores. So let's go to this picture. Macropores are the widest pores. Very easy, very wide. You see here, I say wide, but look at the number, 0.0075 centimeters. It's still very, very microscopic, but we're going to call it as a macro. But because when you compare that with, micropores, they are even smaller, right? 0.003 to 0.0003 centimeters. But you don't need to worry about these numbers. Don't need to by heart anything. I want you to remember there are three pores, three types of pores: macro, meso, and micropores. And I'm showing them in this picture. You see those are big white ones though there? Those are what? Macropores. You see the mesopores, they're kind of little bit bigger, smaller, but you can easily identify. Those are mesopores. And then there is these tiny narrow ones, those are the micropores. Now, why those macropores are white in color? What does white mean? There is air in them. There is no water in them. So macropores don't hold water. Why can't they hold water? Because what does that mean? Why is water draining? What is causing the drainage? Gravity. Gravity can pull the water down through macropores and make them drain. And when they drain, air enters. As soon as water drains, air enters macropores, and that's why macropores are always filled with air. So you need more macropores if you need more air space. What does perlite do? You add perlite, perlite creates more macropores. That's why in that picture, that graph I've showed, sorry, the table I've showed you, the medium with perlite had 38% air space. That's because perlite adds more macropores. So where is water held? Which pores hold water? Micro and mesopores hold water. Meso and micro, both, right? They both hold water. Macropores don't hold water. Remember that, okay? So now you are understanding a little bit more about the pore space. There are three types of pores. Some pores hold air, some pores hold water, okay? So far easy, but as we get towards the end, it can get a little bit technical. Embrace that, okay? Hold on. Yeah. Are holding water, right? Come on. So, can anybody answer the question? You're getting close. Yes, yes. So there are two types of forces acting on water in the pores. I think you both are coming close. One force is gravity. The other force is called capillarity, which is related to surface tension, right? In those pores, capillarity is more than the force that gravity can. Capillarity is upwards, gravity is downwards. An example of capillarity is very simple. You take a glass, you put a straw. What happens to water in the straw? It raises above the level of water, right? Why is water raising above the level of water in the glass? Because of capillarity, surface tension. Capillarity pulls the water upwards, gravity pulls it downwards. In those tiny pores, because their radius is so small, capillarity dominates, not gravity. So the water can be held by two types of forces called cohesion and adhesion. These two are very important. Does it remind you something from your previous classes? Cohesion, adhesion, things like that. Capillarity, surface tension. It's all physics. End of the day, it's all physics. Simple physics. Okay, that's the reason why it is held. Two forces, capillarity dominates in small pores, gravity dominates in macropores. And it's very important that they drain to create the airspace. All right. Now here you can see these three pictures, three different states, three different situations. Situation one, I'm going to call it a saturation. Saturation. Situation two, container capacity, pot capacity. or maximum water holding capacity, whatever you call it. Situation 3, wilting point. All right, I want you to explain to me what are the major differences. Just look, don't read anything here, don't worry about it. Just look at the pictures. Who can start? Okay, first you, go ahead. Filled with water. Agree? Everybody agrees? Okay, then what about container capacity? So the drainage has happened there. Macropores have drained out. Then what about wilting point? Mostly hygroscopic water. All the pore water is kind of drained. So when all the water in the pores is drained and whatever is left over is hygroscopic, can plants get that water? And then when plants don't get water, what happens to plants? They will wilt. And that's why it's called wilting point. What does wilt means? You know wilting, right? Leaves droop, there is no water. That's wilting point. Very simple. Saturation, container capacity, wilting point. So which is the good one? Which is the best one? If we keep it at saturation, there is no airspace, plants will die. By the way, if you have a pot and pot has holes right at the bottom, if it has got holes, then there is gravity effect. Gravity is going to pull that water. There is no way, theoretically impossible, to maintain the substrate in that pot with holes at saturation. No way you can do that. The moment you add water, the gravity is going to pull the water through macropores, so it will never be at saturation. Saturation is only possible in containers which don't have holes. You put soil and there are no holes and keep on adding water, it will get saturated because there is no way water can drain out, right? But when you have holes in pot, it is theoretically impossible. You may get close to saturation, but not 100% saturation. It's not possible at all, right? But this is what we want you to do. By the way, if you work in field and you are more like in agronomy, things like that, there is a term called field capacity. That is close to what we are saying container capacity. Okay, same as that. All right. Okay. Let me see if I forgot something. I don't read this. I keep talking, so I want to make sure that I'm not missing any points. Yeah, something like that. Well, we'll get to this. There are two other things I want to talk about. Available water, unavailable water. So available to plants, unavailable to plants. Okay, what that does mean. So we know that we want to maintain parts at container capacity. Okay, that's the best thing. Here you have 25% maybe airspace and you got a lot of water, so they're all in nice combination, good for roots to grow, everything is good. So plants starts taking that water. Every day they take water, and after 4 or 5 days, all of the water is taken by the plants and plants get to the wilting point. If you don't add more water, they get to wilting point, right? So all of that water from container capacity to wilting point is what is called available water. Just give you a number. Let's say, again going back to your 1 liter example, 1 liter bucket, 750 milliliters pore space in that, okay, and container capacity, let's say, is 60% of that. So let's say there is, and you came up with number 590, right, something like that, water space, 560. So there is 560 milliliters of water. So you have started growing plants. Plants are taking water every day, and then by the time you got to 200 milliliters of water in the pot, the plant is showing wilting signs. Okay, you started at 560, but every day the plant is taking water, right, transpiring, and it got to 200 ml water, and then it starts showing wilting point. So what is available water? 560 minus 200, which is 360. What is unavailable water then? The 200. The 200 is unavailable water, and that 360 is your available water. That 360 is between container capacity and wilting point. Whatever the amount of water that is left in the substrate at wilting point is unavailable to plants, and that volume is called unavailable water. Please. Okay, so our goal is to make sure that The unavailable water is small. You don't want a lot of unavailable water because that water is wasted. Plants are not going to take it. It is held as hygroscopic water. So you want to make sure that whenever you customize a mixture, a soilless substrate, you want to make sure that that unavailable water proportion is really small. Okay, and you will learn how to do that later. But keep that in mind. Available, unavailable. So lot of terms so far, right? Let's revise. Porosity. First thing we learned about is porosity, percentage of pore space. Very simple, right? Then we learned about what did we learn? You learned a lot. Pore space, we learned about pore space. Then we learned about macropores, mesopores, micropores. We learned about container capacity, saturation, wilting point. Then we learned about available water, unavailable water. All these terms should be easy to understand for you now. Okay, when you read it, it should get into your mind. Okay, but now when we started this class in the morning, you said few things about soilless substrates. You said they hold water, they are blackish brown in color, they are light. Now we are going even deeper, isn't it? We are now looking at the physical properties. What is available water in soils? What is unavailable water? Things like that, right? Mesopores, macropores. This type of knowledge will help you to choose the right type of soils. I'm giving you here and there some hints. I just told you, you should select a soilless substrate that holds less amount of unavailable water, right? Otherwise, you have to keep on adding water every other day. Let me explain a little bit more. Let's say you have a soil which has got 100 ml unavailable water, another soil with 300 ml unavailable water. You bring both of them to container capacity. The one with 300 ml unavailable water will wilt in 2 days. The one with 100 ml unavailable water will probably wilt in 4 days. So if the plants are wilting every 2 days, you need to put labor. Keep on adding water, that increases your labor cost. See how that small term, unavailable water, can influence your cost, operation cost. You are a chief operating officer. You should really keep this in mind because labor is expensive, isn't it?
Plus, it might, due to moisture, roots may develop fungus.
Yeah, sometimes root may also, if there's too much moisture, generally what happens is roots are very smart. Roots won't grow into the zone which is saturated. They try to avoid that zone. So they kind of grow up towards upper levels. You know, in a pot, if you look at a pot, almost always at the bottom there is a lot of water, there is no water at the top. That gradient exists because of gravity. So roots kind of avoid that bottom area. They don't want to. They try to grow sideways, things like that. But labor is a big deal. Adding water is important. You have to add water. You may not have enough water, but then you have to add, somebody should be employed to add water. If you are running a 2-acre greenhouse with such a substrate, you will be paying a lot for labor, for sure. So these things have real applied practical value, okay? We may not know that by looking at the substrate, but you will know by understanding the concept. All right. All right, we're getting into the first slide of little bit complicated technical stuff, but this is important. We'll go slowly, all right? We'll try to understand this slide. Here is a graph, and in this graph, I'm comparing a soilless substrate with a regular soil. That's what I'm doing. I'm comparing a soilless substrate with a regular soil. What am I doing here? I'm trying to understand, you add water to, let's say you have a pot with soilless substrate and you have a pot with regular soil. You add the same amount of water, and I'm trying to understand how that water depletes over time. Will the water deplete? Will the plants take water rapidly in one versus the other? How that rate of dry down is happening. You know what dry down means? Dry down means you start with wet conditions, and with time slowly the substrate is drying down. It's becoming drier and drier. I'm trying to understand how the dry down rate is different between a regular soil and a soilless substrate. The reason why I want to understand that is, if the dry down is slower, again I can irrigate them at longer intervals. If the dry down is faster, rapid, all of the water is quickly taken by plants within a couple of days, there is no more water, then you have to irrigate more frequently. So the dry down affects the number of irrigations, the frequency of irrigations, and that's what I'm trying to understand from this graph. I got two technical terms here. One is called water content, the other is called water potential. You will learn about this water potential later on this afternoon probably, or maybe the next lecture. But for now, assume that this is simply the energy of water or the pressure of water. Okay, so if I fill the water all the way to the top in this bottle, there is a lot of pressure because the water is pushing to into the air as well as to the sides of this bottle. There is a lot of pressure. If there is only half water in this bottle, there is less pressure. So more water means what? More pressure. Now here is a trick. These are the units, pascals. Pa is Pascal. Pascal is the unit for pressure. This is MPa, means megapascals. That's all. Kilogram, milligram, likewise it's megapascal. But what is in front of M? The negative number. So if I say, if you go this way normally on x-axis, you will see that the value is increasing, right? Oh, they changed that. Okay. Okay, we'll go. It's too sensitive. Okay. So if we go like this on the x-axis, what happens to any value? It increases, right? From 0 to bigger values. But if it is a negative number, what is happening? The value is becoming smaller and smaller and smaller. That is all I want you to remember. It is a negative number. It is a negative representation of pressure. As you go from here to here, there is less pressure. Simple, less pressure. Meaning you add water on day 1, day 5 there is no water. Something like that. Less pressure. Okay. For now, just understand water potential is water pressure. And in this particular axis, I am showing a negative water potential, meaning as you are going from here to here, it is not increasing, it is decreasing. Just remember that, okay? Water content and water pressure. So I can completely erase this water potential term and I can simply say drying, rate of drying, something like that, as an analogy. The more drying, the less water, right? That's what it is basically, okay? So I'm now looking at this amount of water content is amount of water. Don't worry about these units, you will also learn about them. For this, just simply understand that this is the amount of water, this is how the water is drying in the substrate with time, okay? So what do you see? This blue line is regular soil, the red line is soilless substrate. What do you see? Which one is drying faster? Is the soil drying faster or is soilless substrate drying faster? I want all of you to look at it carefully. Tell me. One of them is drying faster than other.
This is Soilless.
So soil substrate is draining faster at a regular rate. Steep.
So this is soil, right? Blue line is soil, regular soil. This is soilless substrate. Okay. Let's say this is days after withholding water. This is drying rate, right? First day, they are all here. Second day, soil has more water, right? What happened to soilless substrate, the water content? Way less. Within few days, all of that water is gone in soilless substrate, whereas the soils is really slow over time. This is the major limitation of soilless substrates. An advantage and also a limitation. The advantage is that in soilless substrates, most of the water, it holds a lot of water to begin with. You see the line start way up here. The soil line only starts here. The water content is more in soilless substrate. But within a couple of days, all of that water is gone. Plants will take that water very quickly, which means you have to irrigate pots in soilless substrates more often than plants grown in regular soil. You may have already noticed that in your homes. Plants grown in soil, they don't wilt for a very long time. But whereas something in a pot will start showing wilting in a couple of days. The reason is there is a term for that. I don't want you to confuse. It's something called hydraulic conductivity. And I'm assuming that you will learn about that hydraulic conductivity later on from Dr. Prasad in the next week probably. But don't worry too much about that. If you can remember that the water dry down is faster in a soilless substrate compared to regular soils, you completely, you got what you need to, okay? And there is a reason for that, and I will explain that reason also, why it is happening. In a soilless substrate, it is an artificial soil. You have taken peat, you have taken vermiculite, you have taken other things and you mixed them, and you created some pore space. that pore space is got some definite amount of macro, meso, and micropores. But the regular soil is a natural formation, millions and millions of years. And during that time, the regular soil had all radii pores in there. Every tiny pore, so many diverse variations in pore space in the regular soil because of millions of years of soil evolution. This one, on the other hand, you just took 3 or 4 items, prepared it, and you have a soil. So it has some pores, but those pores are categorized into only 3: macro, meso, and micro. So as soon as the water is over in meso, then it goes to micro. That's it. Nothing in between. But here you got one after one after one after the other. Plant roots start taking water, but it's still held in little bit smaller pores, little bit smaller, all the way down. So that's the reason why it drains slowly, because of the continuation of pore sizes. Whereas in soilless substrate, you got 1, 2, 3 pores or 4 pores. If 1 is over, you get to 2, 2 is over, there is no more water. That's it. Because of that, artificially we are preparing them. That's what happens. Remember that that's a major limitation. They need to get watered frequently. You cannot put your plants, add water, and go away for 1 week and come back. They'll all be wilted in soilless substrates. But that doesn't happen in soil. Okay. Again, you end up with the same problem like I described. Loamy soils or anything, and then you also will start losing the benefits. The soils may have pathogens, right? The soils are heavy, right? It may not be uniform. All those problems are there. So soilless substrates, for the same reason, they're just like hydroponic in nature. They just hold water, and as long as you keep on adding water, they're fine. So you have to frequently irrigate. Automated irrigation is the best method to grow crops in soilless substrate. You put a drip stake, turn it on every day, that's fine. That's it. They'll drain very well, they'll give you all the things, good air space, whole lot of water, but you should be adding water also every other day frequently. So just put an automated irrigation sprinkler or a drip stake inside, turn it on by a timer, they'll be fine. Okay, but do not rely on manual. I'm going to ask my worker to come 5 days later and water. Maybe your tomatoes are probably wilting by the time. Okay. Come on. What happened? What happened? Okay, give me a second. It's lecture number 7. That one. Maybe that was the last slide. It's almost 10:30. Okay. Keep thinking. If you have any question, you can ask me. I think there is one last slide, if I'm not mistaken. Yeah, this one. How many more? 2. Oh, we got 2 more slides. Okay, let's do this. Again, this is another example, so it doesn't really matter. You can read through this. What I want to focus are a few more things. These 2 things. So far, we learned about the physical properties of soilless substrate, like porosity, pore space, things like container capacity, wilting point. They're all called physical properties. There are some chemical properties that's also important. Most important chemical properties are EC and pH. We'll learn about them in a separate lecture. But the other ones there are 3 of them. One is called cation exchange capacity. The other one is called anion exchange capacity. So what are cations and what are anions? Who knows? Right. So in terms of fertilizer, tell me what are positive ions and what are negative ions? Magnesium, calcium, iron, manganese, right? Potassium. All of those are cations. What are anions? Most important anion, nitrates, right? Phosphates and nitrates. Do you apply carbonates as nutrient? I haven't taught about nutrients, so hold on to that. But most important nitrates are, no, anions are phosphates and nitrates. So what we are talking about here is, when I say cation exchange capacity, remember I told you all those nutrient ions will be absorbed, attached to the soil substrate and slowly released into solution. We are talking about that capacity. if you have a specific soilless substrate, how much of the anions can it hold? How much of the cations can it hold? Okay. Now, the particles, the solid particles of the soilless substrate, they are negatively charged. Just like clay is negatively charged, the soil particles, the cocoa peat or coir or peat particles, they are negatively charged. If they are negatively charged, what happens to anions? Anions are what? What is the charge on anion? Anions, negatively charged, nitrate and phosphate. So here is a nitrate ion, negatively charged, coming close to the soil substrate. And what is the charge on this one? When negative and negative comes to, what happens? Repel. So soil, sorry, I didn't hear. Go ahead. Well, hold on. That's an important question. So what is happening here? Is the soilless substrate holding anions? Not much. What about the cations? Positively charged ions, iron, manganese, they get attached. So the anions end up in, like he said, in the solution. They don't get attached. So they are available when the water is there, but if you keep on adding water, what happens if you keep adding water? The water in the pot goes out, right? The old water leaches out, what we call leaching, leaches out. What is being leached out with that water? Anions, phosphates, and these anions, when you are leaching them, eventually they go into lakes and ponds. And when nitrates and phosphates get into lakes, what we call eutrophication. You see fish die. You will see some fish die, algae growing. Green algae is there everywhere in ponds. You know why? Because nitrates are being leached out. Clay or soilless substrates can't hold phosphates and nitrates, and that's one of the major environmental problems. So you got to be very, very careful when you're applying nitrates and phosphates. There is an environmental problem, but there is also wastage here. If you add too much water, all the nitrates in the pot go away. Again, you have to add. They go again away when you add more water. So you have to add watering very, very carefully, not to leach more. Each time when you add water, just focus on 5-10% leaching, not more than that. So the nitrates still stay in the pot. Remember, this anion exchange capacity of soilless substrates is very, very small. And that's the reason why nitrates and phosphates can't be held properly in soilless substrates. When they are not held, they are in the solution phase always. And the moment you add water, fresh water, they'll get leached out. You are wasting them, number one, and they end up in ponds and lakes and cause pollution. So we have to be very, very careful. On the other hand, cations are fine. Soilless substrates hold them nice and clean. So that's cation and anion exchange capacity. Okay. There is one last term, you may have already seen this, carbon to nitrogen ratio, C/N ratio, C to N ratio, whatever it is you call it. This is also an important property of a soilless substrate. So why are we interested in carbon-nitrogen ratio? It's all because of bacteria or microorganisms. Okay, when you have this organic soilless substrate, you have a lot of microorganisms. These microorganisms are active. What are they doing? They need energy to grow, and they need nitrogen for protein synthesis, for DNA, for multiplication. You know, replication, DNA replication, things like that. That's what is needed, right? For multiplication, if you want two cells to multiply, they have to first replicate DNA. For DNA synthesis, they need, for protein synthesis, they need nitrogen. Nitrogen is the key factor. Amides are key inside, the nucleases, the DNA helix. So bacteria needs nitrogen for protein synthesis and multiplication. Bacteria needs energy for growth, which the energy comes from carbon. So you have carbon, just give me 2 minutes, nothing. So you have carbon and you have nitrogen. The carbon is important for energy. Bacteria needs, or microorganisms that energy for growth. Microorganisms nitrogen for protein synthesis or multiplication, DNA multiplication, replication and multiplication. So this is what is happening in a soilless substrate because there are microbes. Okay. Now let's look at carbon to nitrogen ratio. Let's say you have a lot of carbon and less nitrogen, meaning carbon to nitrogen ratio is high. The numerator is high, denominator is small, right? You have a lot of carbon, less nitrogen. When you have a lot of carbon, bacteria is growing, they got a lot of energy from carbon, Now they need to multiply, so they start using all of the nitrogen in the substrate. The nitrogen that is present in the substrate, and in addition to that, the nitrogen that you supply through fertilizer is taken by bacteria. Why did you supply nitrogen? Do you want the microorganisms to use the nitrogen? No, you want plants to use nitrogen. But what is happening here? The microorganisms are immobilizing that nitrogen, taking them, making them unavailable to plants. See, if you alter carbon nitrogen ratio, what happens to nitrogen availability to plants? Goes down. The microorganisms now start taking that nitrogen and make that nitrogen unavailable to plants. So you got to maintain a proper ratio. The opposite is also important. Let's say you have less carbon, more nitrogen. What happens is all of that carbon is used because more and more microorganisms are multiplying, and they're all going to feed onto that carbon, get that energy. When they use all of that carbon, carbon is the structure, skeleton of that substrate. When microorganisms use that, shrinkage happens. The soilless substrate shrinks, becomes smaller in volume because it has lost those carbon skeletons. Microorganisms fed on that carbon, and then they became kind of like the whole media is now shrunk. When the media shrinks, its water holding capacity goes down, nutrient holding capacity goes down, airspace goes down. You see the importance of C by N ratio? More is bad, less is bad, because microorganisms play with it. So what you need to do is you got to maintain a ratio of 60:1. That is what we recommend. Just don't buy a media. Ask for this question. When manufacturer comes and says, I have a cocoa peat for you, then ask him, do you know what is the carbon nitrogen ratio? If he says, I don't know, don't buy from him. He doesn't know anything. You now know why the carbon nitrogen ratio is important. If you buy a wrong medium with a slightly higher carbon nitrogen than 60:1, you are immobilizing nitrogen. Your plants won't get nitrogen. But if you do the other way, if carbon nitrogen ratio is less than 60:1, the media is going to always become smaller and smaller and smaller in the parts. That is also going to affect plant growth because there is less water, less nutrients, less airspace. Okay. Again, these terms are so important in practical sense that you have to pay attention. So we started with simply what is a soilless? So it's brown in color, it's light in weight. Now you know so many other things about soilless substrate, right? Their physical properties, their chemical properties. After knowing all of this, you should be in a better place to make a decision on where to buy, from whom to buy, and what to buy. That is what a farmer needs. Farmers need to make independent decisions. Farmers should not rely on a manufacturer telling them, buy this, this is good. Manufacturers are always biased. They want to sell their own product. But a farmer, on the other hand, should be able to make a judgment based on the knowledge they have, make an independent decision. And this is the power of that. The information that you learned today is what you need to know to make a right decision on what type of soil substitution to buy. Because it's a big investment. If I have a 2-acre greenhouse and you're growing peppers, how much soil substrate will you buy? A lot. And you don't want to make a mistake. Now with this background, you have to write down things. You should ask, what is the container capacity of your substrate that you're selling me? Do you know carbon nitrogen ratio? Do you know cation exchange capacity of substrate? If you ask these questions, then that seller is now a little bit, we got to be very careful. They are not at least going to make, at least not going to lie to you at a minimum, because now they know that you have knowledge. That's the purpose of this lecture. That's the purpose of this lecture. You got it? I think we'll stop here. We'll let you, whatever you want to do. Yeah. Okay. All right. I'm actually taking every time 10-15 minutes more, but we started also a little bit late this one. But we'll come back at 11 o'clock maybe. 11. All right. Let's start at 11 o'clock for the next chapter. Next one is going to be easy. All right.